Hello and welcome to this lesson on differential equations. I'm Mohamed Kadem Kari. The PDF of the lesson may be downloaded from the website I indicate here. The outline of the lesson will be firstly to define differential equations, then to consider a very simple differential equation in the form y prime equals a given function g. Then we will present first-order differential equations. Firstly, homogeneous equation in the form I present here, where a is a given constant and y is the unknown function. After that, we shall present equations with the constant second member in the form given here. So the constant second member is the constant b here. And finally, an equation with a general second member, which is some function g I present or I denote here. And the equation is in the form y prime equals some constant multiplied by the unknown function y plus some function g. Let's begin by defining differential equations. A differential equation is an equation where the unknown is a function f from the set of real numbers to itself. Solving the differential equation means that we have to find all the functions that satisfy the equation. Here is a very simple example. We try to find all the functions f such that their derivative equals a constant a. We know that the solutions of this equation are affine functions in the form f of x equals ax plus b, where b is a given real. Indeed, the differential equation generally includes terms with derivatives of f. For example, in the equation here, we have the first order derivative of f. But it can be also the second derivative or even higher order derivatives. The order of a differential equation is the highest order of the derivative that occurs. For example, this equation here is a first order equation. The unknown function f can sometimes be defined on a subset I of the set of real numbers. So it has not always to be defined on all the set of real numbers. Moreover, the unknown function is sometimes denoted y instead of f. For example, the equation considered previously is denoted y prime equals a. Observe, moreover, that we do not always note the variable x here, so we don't write y prime of x equals a, we simply write y prime equals a. Let's give an example now. We try to solve the equation second derivative of y equals a. So to solve this equation, firstly we consider the first derivative of y, and we know in this case that the first derivative of y equals ax plus some constant b. We deduce that the solution of this equation are the second degree polynomials in the form y of x equals 1/2 ax squared plus bx plus c. This formula here comes from taking the primitive second time of this expression. Consider now some given function g, and we try to solve the differential equation y prime equals g. Indeed, this means that we have to find all the primitives of the function g. Here is an example. We try to solve the differential equation y prime equals cosine of x. Then the solutions are y of x equals sine of x, which is a primitive of cosine, plus any constant c. Let's present now first-order differential equations. The differential equation y prime equals ay, where a is a given real number, is called homogeneous first-order differential equation. So it is first order, since there is the first order derivative of y here, and it is called homogeneous, which means that the equation can be written in the form y prime minus ay equals 0, and the term homogeneous means that there is a 0 here in the right hand side. So the solutions of this equation are given by the following theorem. The differential equation y prime equals ay admits as solutions y of x equals k multiplied by exponential ax for a given or an arbitrary constant k. Let's see the proof together. Firstly, we write the equation in the form y prime divided by y equals a, and we know that y prime divided by y may be written as logarithm of absolute value of y prime. So we take now the primitive of this, and we get logarithm of absolute value of y equals ax plus b, which is the primitive of a. Then we take the exponential, and we get that absolute value of y equals exponential of b multiplied by exponential ax. Finally, we get rid of the absolute value of here, and we write y as a constant k with an arbitrary sign, so it is an arbitrary real number, not necessarily positive as given here, because we have get rid of the absolute value. So y equals a constant k multiplied by exponential ax, which is precisely the stated expression of y. Here is a useful consequence of this theorem. The differential equation y prime equals ay admits a unique solution such that y of x0 equals y0, where x0 and y0 are given. This type of condition here is called initial condition in physics. So let's prove this result. We know that the general solution of our equation has the form y of x equals k multiplied by exponential ax for some constant k. But since y of x0 equals y0, we can replace y of x0 by its expression here, and we get that k equals y0 multiplied by exponential minus ax0. Replacing the expression of k now in the general expression of y, we get the unique solution of our equation, satisfying that y of x0 equals y0. Here is an example illustrating these results. So we will solve together the differential equation y prime plus 3y equals 0 and find the unique solution such that y of 0 equals 2. So firstly, we write the equation in the form y prime equals minus 3y. Then by the previous theorem, the general solution of this equation is y of x equals some constant k multiplied by exponential minus 3, which is this term here, minus 3 multiplied by x. Now, since y of 0 equals 2, we replace this in this general form, and we get that the value of k equals 2. So y of x finally equals 2 multiplied by exponential minus 3x. The second type of differential equation we consider in this lesson is an equation with constant second member. This is an equation in the form y prime equals ay plus b. It is called first order differential equation, since here we have a first order derivative, with constant second member. And the term with constant second member means that the equation can be written in the following form: y prime minus ay equals b, where b is constant. So the second member, the right-hand side member, is constant. The following theorem gives the general solution of the differential equation y prime equals ay plus b, so with a constant second member. The solution of this equation have all the form y of x equals k multiplied by exponential ax minus b divided by a. So here is the proof of this theorem. It is very useful since we will use a technique which is very general. Firstly, we start by looking for a particular solution. Here we take the particular solution yp equals minus b divided by a. So let's write that y satisfies our equation and also yp satisfies the equation. Now we subtract the two previous equations and we get this new equation. Let's denote by f the function y minus yp. So we get that this function f satisfies f prime equals af, which is called the associated homogeneous equation. So we see that it is in the same form as our equation, original equation, but there is now the second term b here. This is why we call it the associated homogeneous equation. But this equation, we know that the solution is k exponential ax. So we get that y minus yp equals k exponential ax, which gives the general solution stated in our theorem. Here is an example. We shall solve the equation y prime plus 3y equals 12. And we shall find the solution which satisfies y of 0 equals 5. So firstly, observe that a particular solution to our equation is yp equals 4. So if we replace yp by 4 here, 3 by 4 equals 12 and the derivative equals 0 since the function is constant. But now, since y minus yp is solution of the associated homogeneous equation f prime equals minus 3f, then y minus yp equals k exponential minus 3x. So finally, we get that the general equation of solution of our equation is 4 plus a constant k exponential minus 3x. So if y of 0 equals 5, this gives that k equals 1, and hence we get y of x equals 4 plus exponential minus 3x. In the last part of this lesson, we consider a differential equation in the form y prime equals ay plus some function g of x, where g is given. This is called first order differential equation with a general second member, which is this function g here. This is the general second member. The differential equation f prime equals af is called the homogeneous equation associated to our equation E. Here is the theorem giving the general form of the solution of an equation with the general second member. Suppose that the equation E has a particular solution yp. Then all the solution of our equation E are k exponential ax plus yp. The proof is the same as we did previously. We write firstly that y satisfies the equation and also yp, the particular solution, satisfies the equation. Now we subtract the two previous equations and we get that y minus yp satisfies this equation here. So we denote by f this quantity y minus yp, and we use that f prime equals af. So the function f satisfies the homogeneous equation, which admits as solution k exponential ax. So we get that y minus yp equals k exponential ax, which is exactly the statement in the theorem. Here is an example of application. We shall solve the equation y prime minus y equals x plus 3. So we have a hint in the statement here. Check that yp equals minus x minus 4 is a particular solution. And finally, we shall find the solution that's such that y of 0 equals 3. So firstly, consider this particular solution here. Its derivative equals minus 1. So if we calculate yp prime minus yp, we get this quantity here minus this expression, which gives x plus 3. So we see that yp is solution of our equation. Now, since the difference y minus yp is solution of the associated homogeneous equation f prime equals f, then we get that y minus yp equals k exponential x. So finally, we get that y of x equals minus x minus 4, which is yp, plus k exponential x for some constant k. Now, if y of 0 equals 3, then the constant k equals 7. And finally, we get the unique solution satisfying y of 0 equals 3, which is minus x minus 4 plus 7 exponential x. This ends this lesson on differential equations. I hope to see you in the next lesson. Goodbye.